first question we need to answer when we start talking about this is, what is a graph? A graph is a network of vertices and edges which connect these vertices. And the standard notation for graph, you can see right here, it lists the number of vertices followed by the number of edges. And for this graph here, it's a graph of 10 vertices and 21 edges. And another important idea for this project is the idea of a journey, which is a source vertex and a ending vertex, which need to be connected by some path of conversion. And in this example here, we have a journey going from 0 to 9. And a possible path to connect that would be from 0 to 3 to 5 to 9. And a problem that has already been solved in graph theory is the ability to find the shortest path between 2 points in a weighted graph, which is a graph where each edge has a corresponding weight or distance for traversing it. And one algorithm we can use to solve this problem is Dijkstra's algorithm. And it's similar to algorithms that are used in like MapQuest or GPS devices to find the shortest distance between 2 points on a map. And in this example here, we need to find the shortest path between vertex 0 and vertex 2. And this path goes from 0 to 3 to 4 to 5 for a total cost of 10. And a question you could ask is, what if we allow journeys to share the cost of edges which they mutually traverse? And this is the premise of our project. And this works by, if there are multiple journeys going across a single edge, they will split the cost equally amongst themselves. And it's similar to like a supply problem where if you have 2 packages going from different sources, different destinations, if they can meet up some way along their paths and get put on the same truck, they can save costs, save gas by splitting the cost. And here's how this sharing works in the graphs we're working with. In this example, we have a journey going from 0 to 4 and another one going from 2 to 5. And without sharing, their shortest path would be directly from their source vertex to their destination. And they would each have a total cost of 5. And it would look like this. But if we allow them to share, we'll find a better solution where they can both come, be in the middle, split the cost on the edge from 1 to 3, and each journey lowers its cost from 5 to 4. And playing out that example, we view the journeys as individuals, each making whatever decision they can to lower their own total cost. And this is similar to situations seen in economics, and because of this, we employ game theory, which is used to analyze strategic situations. And one of the most fundamental concepts from game theory is the idea of a Nash equilibrium, which is an outcome of a game in which no individual can improve their outcome given what everyone else has done. And in this project, a Nash equilibrium would be a journey routing where no journey could find a path of lower cost given where all the other journeys are routed on the graph. And when we're finding a solution, first we need to find what kind of solution we want to look for. And we want to find a Nash equilibrium, but a single graph can have many Nash equilibriums, so we need to find the best kind of Nash equilibrium we're looking for. And 2 of the things we looked for was trying to find the Nash equilibrium of minimal total cost and the Nash equilibrium of minimal cost with most journeys, which means the Nash equilibrium in which the greatest percentage of journeys found their lowest total cost within all Nash equilibrium outcomes. And also when we're finding a solution, we need to use approximation methods such as tricks or heuristics that push the graph towards the kind of solution we're looking for. And we need to do this because it's an NP-complete problem. And my work this summer, I developed a way to test if a solution is a Nash equilibrium by asking each journey if it would like to defect from a final solution. And building off this test, I developed an algorithm used to approximate a Nash equilibrium with minimal total cost within the graph. And I also looked into routing order, which is the order in which journeys are placed on the graph and how that affects solutions. And this is all done using C++ programming. And here's a run through of how my algorithm works. The first step, it routes each journey by Dijkstra's shortest path on the graph. So in this example, we have 4 journeys, one going from 0 to 4, one going to 0 to 5, 0 to 6, and 0 to 7. And Dijkstra paths would look something like this. And after we do that, the next step, we go through every edge. And the first thing we do when we check an edge is if there are journeys on it. If there are, we will delete that edge. In this example, we're checking the edge 0 to 2. So we'll delete that edge, take those journeys that were on the edge, and route them on the graph without the edge. So we'll do it like this. And then we will check if that lowers the total cost of the graph. So in this example, the total cost went from 18 to 16. And because of this, we will keep these routings and we'll put the edge back on and continue checking every edge. And after all these edges have been checked in the graph, we will have hopefully a solution of minimal total cost within the graph. And once we're there, we have the journeys defect to Nash equilibrium, which essentially means we ask each journey if it could, given where the other journeys are, if it could improve its cost. And if it can, we do that. And we do that until no journey would improve its cost, can improve its cost, which is the definition of Nash equilibrium. And in this example right here, we have a routing, which is a minimal total cost for this graph, with a total cost of 14, but it is not a Nash equilibrium, because the journey going from 0 to 7 has to go all the way over here, and it has a total cost of 6.6 in this routing, but if it just goes back to its original Dijkstra path, it can lower its cost to 6. And this does increase the total cost of the graph, which is an undesired effect. But the most important thing we need is to find a Nash equilibrium because of the stability associated with that kind of solution. And so far we have tested this algorithm in a couple different cases. We tested it on 2 types of graphs, each with 100 vertices and 10 journeys routed on the graph. And we tested 3 programs. My program, which uses the algorithm I just showed to you. Then the original program from last year, which is similar to my program, except it does not have the journey defect to Nash equilibrium at the end. And then an alternate of my program, which skips the whole edge deletion process and just routes the journeys and has a defect to Nash equilibrium. And here's some of the preliminary results. The 3 things we kept track of was the total cost of solution, the percentage of journeys that found the shortest path with that solution, and the percentage of times the algorithm reached a Nash equilibrium. And in the first graph type we checked, my algorithm had on average, the lowest total cost and was preferred by the greatest percentage of journeys. And on the second graph type, the original program did slightly better in total cost and the percentage of journeys preferring it. But as you can see, it only reached a Nash equilibrium 72% of the time, as opposed to 100% in my algorithm and its alternate. And another thing we looked into with this research was the effect of journey order, which is we found that if we route the same journeys in a different order, we can sometimes find different solutions. And when we're defining a big journey or a small journey, that refers to its Dijkstra cost, the cost of a single Dijkstra path. And in this example right here, it's not exactly how it works, but it kind of conveys the idea we're trying to get at. In this graph, if we route the big journeys first, big to small, it'll look something like this. We have a journey from 0 to 5, which is the big one, 2 to 3, which is the small one. Route the big one, then the small one, for a total cost of 23. But if we route the small one first, the big one can actually play off the small one and share with it and lower its total cost like this, and we'll get a total cost of 19. And some of the preliminary results from this testing, we found that on average, this is without any ordering, but if we order the journeys from smallest to biggest, we find that in general lowers the total cost of the solution, and it has an overall greater total cost when we put the big journeys on first. And the test graph we used, we tested on 11 graphs so far, and each one had 200 vertices, and we routed 100 journeys on it. And future work we'd like to do with this research would be possibly developing more effective testing methods, like finding graphs that really, show how sharing can be beneficial, and possibly combining aspects of previous algorithms, making some kind of Frankenstein algorithm that's a little more effective than the old ones. Another thing we want to look into is the idea of a coalition-proof Nash equilibrium, which is a more restrictive kind of Nash equilibrium. And also investigating whether the algorithm always reaches a Nash equilibrium. So far, we haven't found any case where it hasn't, but we can't prove at the moment that it will always reach a Nash equilibrium. And we'd also like to look more into the effects of routing order on a And I'd like to thank my mentor, Dr. McCulloch, the National Science Foundation for funding, and the other RE professors for making this experience possible. Questions? Yep.
Do you usually run the same size systems with the same number of vertices?
When we're testing, usually test the same kind of graph, the same effects. It'll randomly generate a graph, so it'll be slightly different every time, but we'll run each program on the same graph and, generate a new graph, run all three on it.
But have you run larger or smaller graphs with all three algorithms?
Yeah, we've tried a little bit. There's still a lot of testing that needs to be done. Testing here was kind of preliminary stuff we've found so far.
I just wondered whether some of the algorithms work better for larger systems, larger graphs as opposed to small.
Yeah, depending on especially the types of graphs, sometimes one algorithm will do a little better, and sometimes a different one will do better for a different type of graph. And we haven't looked into how the algorithm perform relative to the graph size, but there could be differences with it.
Could you say a little more about how you got the test graphs and what parameters did you do, or was it randomized?
There was previous to my research, they developed a little program to kind of generate random graphs, and the two types on one of the slides that I mentioned, the graph type 1 and 2. One was I believe a limited directional movement graph, and that's where each journey can only connect the journeys within a certain distance from it. The other one was a threaded grid, which kind of splits the graph up into different levels, where journeys are interconnected on one level, and then certain journeys can connect to the next level, and so on like that. But that's something we really are still trying to develop, like a way to generate good graphs that really kind of exhibit the effects we're looking for.
How do you look for a Nash equilibrium? Do you give each edge a chance to defect? Is that right? To try to reduce its cost? And you just keep trying this, and it never settles down?
Well, right now the graph will,
if it doesn't,
the edge deletion process, first we want to just try to find a solution of the minimal total cost. We're not worried about the Nash equilibrium. And then once we get to that, we try to have it defect to a Nash equilibrium, which usually happens pretty fast in most graphs.
and if it couldn't find a Nash equilibrium, you would just keep doing this over and over and over again?
Well, the programmer runs a loop, and after a certain amount of time, it will stop and say a Nash equilibrium cannot be found. So far, we haven't found a case where that happens. So.
Okay, let's thank the speaker again.